Okay, thank you for the introduction, and thanks to the previous speakers. And so, yes, my name is Marcel. I'm going to talk about storage combinators. Quick about me, I've been in industry for about 30 years, Apple, Microsoft, BBC, and now with that sort of trying to capture that experience into a PhD. Storage combinators in a nutshell. There's a simple storage-based decomposition mechanism. Most of our composition mechanisms tend to be procedurally based. It's inspired by REST, so something that's been somewhat successful and useful. It's a good starting place. And it's been used in practice, and and there's been significant code and productivity benefits that we saw. Significant, not in terms of statistical significance, because in industry we don't get to make those kinds of experiments, but in terms of magnitude and significance of the application. Overview of the talk. I'm going to give a little bit of introduction and background because I think this is maybe a bit left fieldish. I'm going to talk about in-process REST, which is kind of the starting point for storage combinators. I'm going to introduce storage combinators themselves, show some examples, and particular example compositions, because this is supposed to be a composition mechanism, so we need to show those, and then talk a bit about applications. So the introduction background is basically, not to put too fine a point of it, I think we have too much code. I worked at Microsoft. Office is several hundred million lines of code. Nobody understands them. I looked at them, at little parts of them. Closer to home, I worked on Wunderlist, which is a to-do app. And the iOS client was 140,000 lines of code. What's all that code doing? Well, it turns out most of it it's glue code, which we, in the first presentation here, there was some mention about glue code, and it was moving bits around. And like, okay, that just doesn't, for me, subjectively, that doesn't fit. And it suggests that there's some kind of mismatch going on. There's, remember Brooks, okay, is this essential or is this accidental? It smells accidental to me. And in terms of reducing amount of code, I think it's not exactly controversial to say that, yeah, probably modularity is probably some part of the answer. And I took that from the 84 paper by John Hughes, Why Functional Programming Matters. And yeah, small modules can be coded quickly. Yeah, that's good. And general purpose modules can be reused. That's also good. And they can be tested independently. That would be nice. And one thing that struck me about this paper is he then goes on to say, well, if we want to decompose things, we need different kinds of glue, many different kinds of glue. And then he suggests one, which is functions. And, well, 1.5 in lazy evaluation. That seems like, okay, that's when we want many, 2 is kind of the smallest number where you can still use many. And it seems we might need more than that. And in terms of, and if you remember the keynote, there was also some mention of this. That computers really, we don't really compute that much anymore. So maybe the function is not exactly the right decomposition mechanism as well. We certainly store a lot of things. Certainly, on my phone, the apps on my phone certainly do a lot of storage. So maybe a storage-oriented mechanism might be good. And the other thing is, such a mechanism needs to be recursive, obviously, right? Because if you just have one level, from the bits or from low-level objects, that's not going to be good enough. And we've had some attempts then to sort of extend that, from functions. There's obviously John McElroy with pipes and filters, which I think is one of the most successful, in terms of compositionality, is one of the most successful mechanisms. It's just not that applicable. More applicable than we think. So, for example, the move to reactive systems, that's a lot like that. So that's good. And of course, a big one, certainly also in the context of this conference, Alan Kay's vision of objects. And he in this History of Smalltalk conference paper, he mentioned that he envisioned it as, a network of computers hooked up by a very fast network, thousands of computers hooked by a very fast network. And that was his idea of objects. And then just scale that down into a single computer, because then you have a mechanism that can obviously scale back up. Now, I think that's a very good idea, taking things that we know work in large, scaling them down, and then we know we can scale them back up. There is a caveat there, is that he didn't actually have thousands of network computers, so this was a Gedanken experiment, right? And it turns out that when we tried to actually do that scaling back up, Corba, ring a bell, SOAP, it didn't really work. And there's another couple of problems, that the mechanism is still kind of procedural. I mean, we hook the procedures to the structures, but they're still procedural. And when we actually started to compose objects together, there are frameworks, and frameworks are not objects. And they also don't compose really well at all. So, you know, it's a very good idea, and certainly good basis, right? I mean, it's done a lot, but maybe not quite what we wanted. So it does, nowadays, we actually do have a very large network. It's called the World Wide Web, the internet, with billions of connected computers, and most of them happen to talk REST to each other. That's how they connect. And the idea that I had was, well, okay, that, you know, Alan had the right, that was the right thinking. Let's just take that, the one that we do know works, and scale that down. And that's in-process REST. And that can be supported by polymorphic identifiers, which are just URLs, pretty much. And there's some previous work. There was a system done at the BBC in about 2003-ish time frame, and there's a book chapter on in-process REST, 2014. And we took a feeds application that was distributed but not REST-based, and we kind of inverted that, made it non-distributed and REST-based. And the results were pretty good. We reduced the code by 4x, increased the media output by 3x, the number of sports, it was a sports feeds application, by 2x. The number of processes was reduced by about 100. Performance was increased by about a factor of 1,000. And reliability was improved by a factor of 100. And the team was much happier, and that's very good and productive. It was implemented in Java, so actually, you know, you had to deal with a lot of string processing. So it was really, you know, the language was really just supporting a meta language that we actually programmed the system in. And then, so a little later, I added some language support with polymorphic identifiers that support this in the language. And just a quick idea of how polymorphic identifiers work. You have essentially URLs in the programming language. Every identifier is a URL, and then, so these are two examples, and they get evaluated by scheme handlers. One is a variable, so it goes in process and looks up in memory. The other one says, well, it's HTTP, goes to the HTTP scheme handler, and goes to the web and retrieves the object. So it's all unified. You can do file systems, databases, whatever, custom stuff. And that's actually mediated by a very simple mechanism. And that's a theme of this talk. This is really simple stuff, easy to understand. Just pretty much the HTTP verbs as an object-oriented protocol. That's get, right? That's put, that's merge and delete. And it's actually compatible with mostly compatible with the Smalltalk dictionary protocol. So we now have a mechanism that's storage-based, but it's not recursive yet. Storage combinators make this recursive, and this is also really, really trivial, right? That's a store, scheme handler, and a storage combinator just says, well, we implement the storage protocol, but we also use it to get information from somewhere else. And that's about it. If you remember anything from this talk, that's it. Simplest storage combinator is just a pass-through. This is syntax is sort of Smalltalk-ish. It's a subjective Smalltalk. And it just implements the verbs. And so and they all delegate to their source object. So self-source blah, 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 same thing. So again, trivial. And so we get some example combinators. Now this is not an exhaustive list, but it's some that we have found useful and the ones that are sort of generic. Usually when you're in an application, you also have some application-specific combinators that you combine the two, and then you get something useful. technology. And it grained. I might have been holding it wrong. Oh. Okay, restart. Yeah, so this is a hierarchy. That's sort of the basic abstract store class. Here's some non-combinator-based stores. And these are some of the storage combinators I'm going to briefly introduce. They sort of fall into a couple of groups. One is sort of just mapping. They just map the inputs and outputs and the references. Then there's ones that combine several stores and combine the results. And then there's logging, which is kind of interesting. Mapping, very simple. Things like, I want to transform from and to JSON. I want to serialize this stuff, typical in storage. Another one, you can transform the references, and I'm going to show that in a second. And the way that the mapping stores work, basically they introduce these additional methods. Map the references, map retrieved object, map objects that you're going to store. Again, very trivial. And then the methods from the protocol are just crap. Wrong one. Well, they just delegate to those. It's simple enough. Oh, I had the same slide in there twice. Okay. Yeah, these just then delegate to the methods we just defined. And again, it's a fairly trivial mapping. And then if you want to implement one of these stores, the relative store, well, it implements one of these methods, the ones that maps the reference, and it just adds the prefix. And what that allows you to do is do some scoping. So for example, I want to get a new scheme going. That's the home scheme. That's my home directory. Well, I can just say, well, get me the reference to my home directory, get a relative store, hook these together, and then I have a home scheme that I can use without reference to the full path. So combining, we have a few. There's a cache, which is very popular. Switching store just says, I'm going to select from one of these stores. The sequential store, which does a search. Searches through several stores for the answer, and it stores to the first one. And I'm going to just briefly show you the caching store. The central point pretty much is the copy from source to cache, which is, well, I'm going to fetch from my source, and then I'm going to put the result in the cache as well. Again, it's not rocket science. And then the whole cache just uses that for the get. The put obviously has to put it in the cache and the source, and the merge is very similar to the put. And then we get some additional handling for deletion and invalidation, which just deletes the cache. The logging store, I'm not going to show in code. All it does is log operations to a polymorphic write stream, which I talked about at DLS. Surprising applications. One, of course, logging and debugging, but also keeping multiple stores in sync. For example, a backend. You just have the URLs and the operations rolling by, and then you can slowly send those to another store. And also, very similar, actually, MVC notifications, keeping the UI in sync. With that, we can do some compositions. First, a node on notation. Then I'm going to show a storage stack, and then an asynchronous version of that storage stack. Notations. There's a textual notation, which is the one we had just seen for the home directory. Then we put that into a caching store and hook that up to an HTTP server. So we have an HTTP server for our home directory that has an in-memory cache. And completely equivalently, although the arrow is pointed in the different direction, the graphical notation. And the graphical notation is actually derived automatically from the in-memory representation, which also goes to show you that this is a very simple mechanism, because the graphical notation is a one-to-one mapping, which is not often the case. And in addition, there's an array-based, which is kind of Lispy notation for programming languages that don't have direct support. So one possibly interesting composition that's actually very common is a storage stack. We use that in Wunderlist and Microsoft To Do, for example. And that means you just have a caching store, you have an in-memory store, and then a serializer and a disk store. And actually, you probably have a relative store in between, but I'm not going to show that. And that just means that when, for the application, the storage is a unified store, and it will get things from disk if it needs to. Otherwise, it will get it from memory. And if it stores, well, it'll store it to memory and to disk. One problem with that, of course, is in this formulation, it's synchronous. So writes to memory are going to be limited by disk speed. So in addition, we have the asynchronous store. And there's sort of the same elements. There's the caching store. There's disk, JSON, and memory. And then there's a little bit of magic in between. Right? Reads work the same as before, but writes go to memory. And then instead of going directly to disk store, they go to a logger, which then discards the write. The reference goes into a queue. And then there's a copier object, which asynchronously reads the references it gets from memory and stores them to disk. And what I find neat about this is that essentially, this is fairly complicated behavior, which is constructed just by plugging these things together. And once you know that the individual pieces work, you know that the composition works, and it worked out of the box, just plugging things together. So, having shown some of the storage combinators and how you can plug them together, here are some actual applications. In Wunderlist, we started fairly small. We hadn't really wanted to use storage combinators as such. We didn't really think of that. We just had a stand-in because we had a storage stack based on core data, which was very crashy and used a lot of code and a lot of rework to make it work. But after a while, the stand-in, the temporary solution, worked so well that we started expanding it. So the core is the stand-in for the application. That's the caching store from basically the storage stack. Pretty much the same structure here. But in addition, there was a switcher here because we had some sensitive data, like user data. And sensitive data went into the keychain, which was also wrapped with a store. And then we have the rest of the storage stack here. And what was really nice is that for testing, that was we could just replace it with this, and it worked the same from the application point of view, right? And so the tests were really fast and simple. And because it's all just compositions of things, of these store elements that work the same way, we had a high confidence that that if we tested it, it would also work with the combination. And the result was that the storage-oriented code that we had, even though we were using a Apple-provided ORM, was dramatically reduced. The number of crashes, most of which were storage-based, was with Wunderlist 3, the release was reduced by a factor of 10x or more. And performance, we didn't really do any measurement because we didn't have to. It was a problem before, and it just never became a problem again. So in To Do, we went a little further. I'm not going to explain this in detail, but we started putting a lot of the application functionality into these stores. But the basic structure is still there. There's the core, there's the disk stack, and then in the middle we have some application-specific functionality. And so going back to modularity, this was some of the feedback from developers. So storage combinations could be turned on and off on the fly, great for feature toggles with rapid development. There was a unit interface, so the developers knew how to talk about things without having to reinvent new terminology all the time, and without having to write new glue code all the time. because the pieces would always just fit. And then, of course, combine the work together. Oh, gee, composition, modularity, yes. And of course, yay, less code. Some of the things were rewritten with less than 50% of the code. The estimation was we could rewrite the entire app in less than 50%. And actually, I talked to one of the developers later, and that was a sort of the written response. And he told me privately that actually it was more like 10x, but he told me 2x because 10x would be just not believable. And it probably isn't, so, your call. And of course, testability was improved dramatically. So, outlook. Having a non-procedural, of course, procedurally implemented, but non-procedural mechanism does mean that, for example, your typical procedural debugger is not going to be very useful. That's a problem on the one hand, but it's also an opportunity because you can actually debug things at a much higher level. And of course, we have a graphical representation that's really one-to-one. You can certainly use that to construct things meaningfully. We have some linguistic support. More would be nicer, for example, for creating these storage combinators. Most of the support now is for plugging them together. And of course, more implementations. This has been implemented in Objective-C, used in Swift. We have a Smalltalk implementation. There's one in JSON with the Lively project. But this can be used in any language. It's just nicer when you have linguistic support. But it's extremely useful without it. And of course, more usage. I'm certainly going to use it more. I hope other people are going to use it more and give me feedback. And that about wraps up my talk. So we have a storage-based composition mechanism that's more aligned with what applications do. It's REST-inspired, so something very useful and successful, and we scale it down. It reduces the architectural mismatch between what we do and how we implement it. It works in any language, but of course it's best in Objective Smalltalk. Thank you. Any questions?
Should your storage combinators replace the collection classes? And what does that tell you about, programming language paradigms?
I haven't fully thought about that yet. Certainly dictionaries are not interested because storage combinators are mostly a key value mechanism, so just an ordered collection. They do use, I've used ordered collections and arrays a lot in the implementation, so there's a good question whether that's integrated. I do think, yes, computer languages are missing something there. I think the whole idea of storage has been neglected. There's a quote by one of the early Smalltalk guys is that, once you're inside the object, it's just Pascal. That's sad. I did notice that, for example, when you look through some of the APIs, for example, Cocoa, the variety and just sheer bulk of storage-related methods, message sends, is just enormous. And with storage combinators, you can pretty much get rid of all of that and just make everything much, again, more composable and just simpler because it's always the same mechanism. So I don't know if that answers your question.
So you have this very nice storage-based composition mechanism, and you said it's REST-inspired. I wonder how, is there something about REST that makes it essential? Or could you do the same thing with, say, GraphQL or some other, is there something about REST that is essential?
Well, REST, you talk about, can you do it with URLs? One of the key components of REST is URLs and verbs, right? And there's actually, wonderful. Roy Fielding in his dissertation actually does talk about why did Corba not compose and why did REST compose? And the key is having a small number, not one or zero, but a small number of verbs that have sort of fixed semantics, right? You know what a get is. And then you can have intermediaries because they know what a get is. Whereas if they have some random message send, they have that you can't do an intermediary because it has no idea what the semantics are. And the interesting thing is, when you look at applications, is that most of the application semantics we want are actually that simple. And that means, yeah, that this is actually a close enough match to what we want to do, and it has these nice compositional properties. Now, again, Unix Python filters essentially has, well, you might call it 0 or 1 verbs, or you just have the vertical pipe, and that's why everything composes, right? It might not do what you want, but you can put them together. This is very slightly more complex, so you can still put the things together pretty well, and you still have a pretty good idea that it does what you want.
Thanks, Marcel. That was really nice. I was thinking, when you have simple components and you plug them together, then you often get the situation where there are some cases where it just works perfectly, other cases where it just does something weird that isn't quite what you wanted. And I wondered if you had any examples of that, you'd encountered any instances of that with your work here.
Yes, a little bit. So certainly the cache, and particularly making it asynchronous, there's like, oh, okay, yeah, that's a little tricky. They work themselves out much more quickly than I would have expected. That's one of the reasons this is a surprising discovery. Wait, this works? That's too simple. It can't possibly work, but it seems to. And I haven't had really, and I would have expected exactly the same thing, but not very much. Yeah.
Thanks.
Yeah.
Very quickly, what about concurrency?
Yeah. So I've done nothing in this. These are single-threaded. There's certainly with this, well, actually, the async writer is a little bit, right? That does some concurrency. Yes. So, for example, certainly transaction handling or locking can be implemented as a combinator. So that shields things that are underneath. But otherwise, mostly single-threaded so far, and I haven't really thought about it because it hasn't been necessary. This is very much driven from use.
Questions? All right, let's thank Marcel again. Thank you.
Thank you. And everybody have a good lunch.